We're here primarily, of course, to celebrate Steve Kahn's 60th birthday. While I personally struggle immensely to believe that Steve will be 60, I don't doubt that we will be able to celebrate that idea well over the next couple of days. We have a really fantastic science program ahead of us for the next 2 days, spanning many of the main frontiers in experimental astrophysics. The talks will be given by many of the leaders, the foremost leaders of those fields as well. So for the students in the room, I can promise you that the next couple of days should be a really good investment of time. Without further ado, since we started a couple of minutes late, I'd like to introduce you to our acting director of KIPAC and our new division director of particle astrophysics and cosmology at SLAC, Tom Abel.
Okay. All right. Wow, this is great. Welcome. This is KIPAC, 12 years old, this place. All we have to do is wait, right? Time goes by. But what Steve and Roger built here is just tremendous. What I want to do is I want to first start out, with something we usually leave to the end. I want to thank some of the people that actually helped put all of this together. This way we can appreciate them during the part as well. And so first, actually, Steve Allen took this job on with vigor, and that's why it's turning out so well. John Skinner and David Stricker have been helping a lot. Sha Sang, Ping Feng, Koi Hun, Jennifer Conan-Tice, and Rosanna Yao. We already saw them outside. Everybody's helping there. Let's see. We have Martha Siegel, and she's like the soul of the institute. She just it's the joy and the pleasure she has that helps us all have a wonderful environment. There's Siba Madavi that's really helped always put these things together. With her, I would say that whether it's a snake pit, a beach vacation, a cocktail party, I'll go anywhere with her. And then we had a home advantage. We had a home advantage because we had Susan on the local organizing committee and really helping this event tremendously, and I think you'll get to appreciate that over the next couple of days. For the SOC, we had Tony Tyson, Greg Medeski, Bruce McIntosh, Fiona Harris, and Claude Conessaris, Roger Blanford, Phil Marshall put a lot of effort in here as well, Andy Rasmussen, and to get things really started, it was a lot Fritz Perels and Steve to really make this work. So I'm tremendously excited to have all this going on and get to enjoy these next 2 days with you. The universe has been totally great to us. I mean, it's absurd. It didn't have to be that way. Every time you build any sort of detector, you put it wherever you want. I mean, we have some folks here that put it on the ground. Look for dark matter there. Steve doesn't care. He puts them anywhere. Like he puts them, whether it's on a satellite or in Chile on a mountaintop, or whether it's a laboratory, in any basement or any other room he can find. But the universe has been absolutely amazing to us. No matter what you do, whether it's the infrared, whether it's the X-rays, and tremendously for us here as the gamma rays, we have been surprised, and every time. So when I look around, and if you look at what KIPAC is today, 12 years in, the breadth of this is just stunning. And to me, to be able to work here and interact on such a broad range is intellectually just tremendously stimulating. And we have a particular environment here at SLAC and at Stanford that just makes this place work. There is, wherever you look, there's just so much interesting stuff going on. It's like a candy store. Little bit, if you were to try to eat everything, you die. It's too much. I've actually been growing too, a little bit like the universe. But anyhow, I think we're very proud of what happened here. We're very thankful to your contribution, Steve, to this. And the beauty is, this also the next 10 years will be just totally amazing. And we'll hear many reasons why that we know that to be true. And all right, let's celebrate that. And the first talk that we're going to have actually is beautiful because it is a person that really had a lot to do with us being able to be here now in this building, having this institute, having all these people around. So welcome again, and we'll have Jonathan Dorfan next. Oh, I can already see him. Okay, thanks.
Hi, good morning, everyone. Are you able to hear me? Well, it's my great pleasure and honor to be the opening speaker at the celebration of the teaching and research career of Steve Kahn. My sincere apologies that I'm unable to be at the fest in person. I ask for your indulgence that I come to you electromagnetically, and that it being 2 a.m.-ish here in Okinawa, my visage will disappear soon after my talk ends. The theme of this fest, as it should, highlights science, recognizing that Steve is driven by knowledge creation and by the culture of discovery. Perhaps a bit anomalously then, my words are more focused on a journey. How Steve came to Stanford, his contributions broadly to Stanford and to the community. Happily, however, it all very much begins with science, indeed the science of astrophysics. It was early 1999, about 9 months before I was to assume my designation as director of SLAC. Negotiations regarding GLAST, as the Fermi telescope was then called, were getting complicated both locally between SLAC and the main campus, but also in Washington, which was contemplating how to approach its first major collaborative venture between DOE and NASA. Since these issues were to become my responsibility, I suggested to then SLAC director, Bert Richter, that I assume the GLAST oversight role that he was performing. As I remember it, Bert had little hesitation about relinquishing the reins, and I took over the SLAC stewardship of GLAST in March 1999. My solution for the SLAC campus sharing was rather different than Bert's. I presented my plan, GLAST at Stanford, Blueprint for Success, to then Stanford Vice Provost for Research, Charles Kruger. He seemed to like the approach, and we adopted it. The key element of the plan was that we would use the SLAC physical infrastructure for the assembly and the testing of the lab. SLAC Building 33 seemed to me an ideal choice for the GLAST activity. At this stage, GLAST was not yet a funded project. A few days later, I took GLAST PI Peter Michelson over to Building 33 to warm him to the idea. As we walked through the building, I realized that we could plan beyond the GLAST era by dedicating the building long-term to particle astrophysics experiments. The needed modifications to the building, I thought, should be accomplished so as to position SLAC competitively for telescopes and other instruments that would inevitably follow GLAST. I became enthused by the scientific opportunity that would inevitably be the larger and more permanent involvement by Stanford in astrophysics and cosmology that this represented. The experience of walking through Building 33 that day seemed to have a somewhat different effect on myself and Peter. Peter seemed relatively unimpressed by the building that I proposed for his experiment, and my head was swirling with ideas of an institute. By the end of the day, the idea for a Stanford-wide Particle Astrophysics and Cosmology Institute had crystallized in my mind. I reckon that between the main campus and SLAC, we had exceptional technical and physical infrastructure assets. If we could combine this with a vehicle for faculty appointments, it would allow us to enhance our academic talent and leadership. We could establish a powerhouse for astrophysics and cosmology at Stanford. We needed a way to concentrate that activity. We needed a building of sufficient size to house the institute. We needed what later became known as KIPAC, housed in the Kavli building. The SLAC faculty strongly endorsed this idea. Their April 2000 faculty development report, which was chaired by the late Bob Seaman, stated, to position Stanford to best take advantage of the opportunities in this field while building from the existing Stanford resources, we recommend establishing a Stanford initiative in particle astrophysics and cosmology involving applied physics, and SLAC. One might envisage an institute with a total of 8 new faculty positions, the report read, which are joint appointments between SLAC and the Stanford campus. On April 11, 2000, Bob Seaman and I sat down with 3 faculty chairs, Steve Chu for physics, Bob Beyer applied physics, and Charles Prescott at SLAC, to begin the cooperative initiative. A tri-department committee was formed to establish the scope and parameters for an institute. Not surprisingly, their leading recommendation was to hire a director for the institute. And in the 2002 academic year, a committee was formed to do an international search for a director. The committee was chaired by Doug Asheroff and the late Martin Cook. It has as its members Elliot Bloom, Les Cabrera, Lynn Kaminsky, Lance Dixon, Roger Romani, and from Berkeley, Chris McKee and Bernard Sadula. I remember quite vividly, after a while, being approached by the committee saying that they had not one, but 2 outstanding candidates, and they wanted to hire both. Ringing in my ears was the admonition we younger generation SLAC faculty had endured many times from Dick Taylor. Making 2 appointments when 1 billet was available because you don't have the resolve to choose from amongst 2 strong candidates was shying away from disciplined academic management, he would have heard. Well, thankfully, strongly backed by the president and the provost officers, Stanford took the bold approach and decided to go after both candidates, Roger Blanford and Steve Kahn, a world-leading theorist and a world-leading experimentalist, the dream team. What followed was an exhilarating few months of dual recruitment, fashioning individual packages for Steve and Roger, but at the same time coming to an understanding and agreement that allowed them to co-lead KIPAC. It peaked during the Christmas break in 2000. I recall Persis and myself closeted in the SLAC director suite, tracking down Roger and Steve for pivotal phone calls. Steve turned out to be the more challenging to connect with that Christmas. It took us a while to learn that he and Susan were in Israel. Steve was visiting and lecturing at the leading Israeli institutions, Hebrew University in Jerusalem, Weizmann in Rehovot, Tel Aviv University, and the Technion in Haifa. But track him down we did, and on January the 15th, 2003, the Kavli Institute founding gift was announced, with Roger as the inaugural director and Steve as the inaugural deputy director and assistant research director at SLAC. Steve and Susan arrived at Stanford in July 2003, and Steve took up his joint faculty appointments, 50% in the physics department, 50% at SLAC. And 11.5 years later, he continues to serve those 2 Stanford constituencies with equal zeal and equal effectiveness. From the very beginning of his tenure at Stanford, Steve believed very strongly in the importance of the SLAC main campus relationship. As I will mention, both SLAC and the physics department have benefited singularly from Steve's ability to multitask, his dedication, and his extraordinary leadership. But more than that, while it has not always been straightforward or easy, Steve has been one of the mainstays of ensuring the growth and long-term success of the SLAC main campus partnership broadly in physics. In 2003, KIPAC existed only in name and intent. There was a founding gift, a visionary plan, and 2 leaders. The vision had to be made concrete. There was a building to be designed and built, faculty and staff to be hired, additional funding to be attracted, etc., etc. And critically important was a need to create equally powerful theoretical and experimental programs. It is hard to overemphasize the breadth and effectiveness of Steve in those early KIPAC years. The task was enormous. Yet additionally, Steve taught in the department. He carried on with his own research, principally as the USPI on XMM Newton, and he even helped out glass with a knotty cabling problem, although I'm not sure that was his shining hour at Stanford. Steve will remember. DOE was ambivalent about committing funds to KIPAC, to astrophysics particle instruments, focusing too narrowly, at least for my taste, on a restrictive definition of the HEP mission. Moving beyond the glass commitment was very challenging, and Steve's leadership in so successfully getting Kavli firmly rooted in the observational game was essential. I could and probably should have spent more time on his role in building up Kavli as Roger's co-lead, but there's a lot of ground to cover in Steve's journey with Stanford. In short, Steve more than delivered on his side of the dream team. In the wake of the accelerating universe discovery, Steve saw, perhaps more clearly than others, certainly me, that the breakthrough throw-deep instrument, the one that would outrun the competition for community support and funding, was LSST. While he rationalizes my slowness at choosing which alternative SLAC would support as associated with exercising measured judgment, he would have liked me to have gotten to that point significantly earlier. Sorry, Steve. However, despite all the commitments and the responsibilities in those early years, he doggedly and effectively maintained SLAC's role and his 2004 to 2013 role as deputy project leader and camera lead scientist. The culmination of that excellent judgment in picking LSST, his innate ability to lead his scientific and technical colleagues, was to have been chosen as the director of LSST in 2013. The project could not be in better hands. I have little doubt that LSST will play a pivotal role in our ultimate understanding of the fundamental physics of our universe. In 2007, I asked Steve to take on a quite different job as SLAC's Associate Director of Particle and Particle Astrophysics. A daunting task for a non-high energy physics scientist. He negotiated his role hard, as Steve does, but never put in doubt his willingness to take on the job. He served for 3 years, the latter half under Percis's directorship. These were very challenging times in the SLAC-HEP DOE relationship, and Steve served the lab outstandingly well in that role. He had the most undesirable task of accepting and then administering the premature shutdown of the B factory. Working with the Baba spokesman, Hassan Jawahari, Steve helped to fashion and broker a very effective additional 3 months of running off resonance, which provided a very effective physics-rich non-CP violation program. Again, throughout this period of novel and challenging leadership, Steve maintained his on-campus and LSS teaching and research roles. In 2010, he was elected chair of the physics department. I was not on hand to observe this period of Steve's leadership at Stanford, but a wise and experienced colleague from the department described his chairmanship to me in glowing terms as being successful, effective, as having initiated additional department funds, while wryly pointing out that administering the likes of the Stanford physics faculty is not always the easiest task. As if all these high-level, high-impact roles have not been taxing enough, during his time at Stanford, Steve has been an invaluable contributor to the scientific community at large. He lectures widely. He served on the 2000 McKee-Taylor Decadal Study. In 2006 to 2008, he successively served as vice chair, chair-elect, and then chair of the APS division of physics. He named but a few such areas of service. One cannot but admire the impact that Steve has had on Stanford, both at SLAC and on the main campus. But as I emphasized earlier, Steve has always been committed to the critical importance of the partnership. He echoed that when I spoke to him to prepare for this presentation. His parting, unsolicited comment to me was that he would not have moved from Columbia to Stanford had it not been for the possibilities provided by the combination of SLAC and the main campus, and that he remains of that strong resolve. How fortunate that Stanford has been to have taken that bold step of filling one billet with two appointments. On a personal note, I would like to add I did not know Steve before he came to Stanford. But for me, it has not simply been that it was a highly successful recruitment. Rather, I feel the richer for his scientific and managerial collegiality and wisdom, for his and Susan's friendship, and for always spicing things up with that somewhat mischievous delight he takes in life and its foibles. And yes, for that ever-present engaging smile. Steve, Renee joins me in sending our warmest congratulations to you for the most deserved celebration of your time so far at Stanford. We wish you many, many more years, and we wish you a happy 60th birthday. Thank you. Yes, I hear you well. Thank you. Hi, Steve and Susan. Nice to see you down there at the front.
Have a good night's sleep now.
I will. Thank you. Good night, all.
Okay, so we have Ken's talk in here. So next up we have Kent Irwin. There he is.
Am I live here? Sound-wise? I could go to my office and Skype if that would be more comfortable.
It's a high-tech institute. I can echo Jonathan's statements. I remember being on the faculty of KIPAC Forum, and when we were recruiting
KIPAC, yeah.
Roger and Steve, and the day that we heard that they were actually going to come, and we were all terribly excited to have the launch of Roger and Steve here. We had the meeting.
So I should use up this extra 20 minutes, I presume? Get into great detail. I'll rederive everything from first principles. Okay.
Okay, so next we're very happy to have Kent, who's going to talk about thermal detection.
Okay, so thank you very much for the invitation. It's really a great honor to be here. The kind of small section that I was put in for this was called returning to California. I think that's referring to the migratory patterns that to some extent both Steve and I have shared. So I thought we'd explore those migratory patterns. This is me. This has nothing to do with you. So I started in Colorado and actually came out to be an undergrad at Caltech, a grad student at Stanford in California. But I ended up returning to Colorado for the next 20 years or so, and have only recently, like in the last year and a half, returned back to Stanford and SLAC. And I thought that was kind of an interesting thing. But Steve has been much more repetitive in his migratory pattern. I don't actually know where he started, but as an undergrad, he was certainly at Berkeley and migrated to Columbia for grad school and also beginning, or is that backwards? Backwards. Anyway. But anyway, he went many times back and forth. He was at Columbia as a professor. He was at Berkeley as a professor. Columbia as a professor again, I think. And then finally being back here. Anyway, it's a very complex migratory pattern.
The answer is that I like New York and Susan likes California.
I see. So she's winning now. That's great. There's also been a scientific migratory pattern. And here's the migratory pattern we're all familiar with in California, of course, is the monarchs. That's more of a north-south sort of thing, which usually makes a lot more sense than east-west. But Steve has actually migrated scientifically in a way that I have some commonality with as well, from doing X-ray spectroscopy as a specialty, broadening that out into cosmology, and now with all of LSST, there's lots of other things with transient science and near-Earth objects and such. And so we've always run into each other because I started out doing dark matter. That's kind of on the side as a grad student here with Blas Cabrera, but then developed the sensors that I'll be describing for X-ray spectroscopy. So we would run into each other at many, many meetings for many, many satellite experiments that never actually flew. I don't know how many, but many. I then have also broadened into cosmology, and both of us have moved to this beyond. In my case, also looking at doing X-ray science here at SLAC for condensed matter chemistry and biological applications. And I think what we'll see throughout this workshop is that actually this scientific migratory pattern covers a lot of the talks that will be in this 2-day workshop. There'll be a lot more discussion about X-ray spectroscopy and X-ray astronomy, I think in the next session. Cosmology with many different types of cosmology, the other applications of LSST, my little dark matter stub Tom Schutt will be talking about, but that also features into cosmology. But I think that this kind of like overview covers about everything that's going on in this workshop. So I'll refer to a few of those things as we go. So as I said, we both started doing X-ray spectroscopy. X-ray spectroscopy is a very, very rich tool to study astrophysics. And it can probe many, many different things, active galactic nuclei, supernova remnants, all those sorts of things. I'm just going to pull out one particular example because the next 2 talks I think will go into a lot more detail about X-ray astrophysics. And that's one that's particularly interesting to me, which is studying galaxy clusters. And of course, a lot of what we see in the universe is made up of hot astrophysical plasmas. That what's between all the stars and planets and things is plasmas that are often at millions of degrees. And this can be within galaxies, within galaxy clusters, actually at very large scales. And whenever you have a hot cluster, it emits in the X-ray. And so by looking at these X-ray frequencies, you can learn a lot about these large-scale structures. And clusters are very interesting because it's the largest, gravitationally bound structures in the universe. They're an interesting probe not only of astrophysics but also of cosmology, and that's something that, of course, Steve Allen is one of the world leaders on, is using these things for cosmology. So that's just actually an optical picture of a particular galaxy cluster, and this is from one of Steve's 2004 papers. Doing some of the cosmological constraints by combining things like CMB datasets and supernova 1A and clusters. And this is an active and continuing area of research, but that's just an example. But it turns out that clusters are actually very difficult to use for cosmology as well because they're rich astrophysical objects. And really what you want to do is just get statistics from them, just get a mass and distribution for cosmology. but they are complex structures that have mergers, active galactic nuclei outbursts, feedback, shock fronts, and there's a lot of still things that still aren't fully understood about how galaxy clusters evolve, how they cool, and X-ray spectroscopy is a wonderful probe of that. And as we said, X-ray or plasmas that are million-degree plasmas, emit a lot in the X-rays, and they also not only emit with what you'd initially think of Bremsstrahlung and recombination type lines, but every element, every ion, every highly ionized ion is going to have separate features that are going to have structure to them, that are going to have different sort of redshifts, and by studying them, you can actually pull out, by fitting to these elemental lines as well as to the underlying Bremsstrahlung, you have an enormous rich array of data that you can pull out. You can try to understand the temperature, pressure, turbulence, abundances of all the different elements, disequilibrium, and it's an incredibly powerful tool to understand these complex beasts that are galaxy clusters. So, and the two satellites that have been the most powerful for actually studying these astrophysical phenomena are things that Steve is definitely has used to great effect and has been a strong contributor in developing this capability. And these are the Chandra mission and XMM, the European mission, both that carry grating spectrometers, which are wonderful beasts, but they're also terrible. They're wonderful because they have incredibly high resolution. They allow you to really probe this X-ray spectroscopy at the level to start trying to understand, like with clusters and AGNs and everything, all these incredibly detailed models. Because each one of those lines is an additional set of information, and you can combine it all and have amazing constraints. But they're incredibly inefficient. They're sharply limited for imaging extended sources. So you can take a big cluster and you can study a small section of it, a line or something like that, but at this point it's difficult to image large statistics, large numbers of clusters, two-dimensional images, which is what you'd want to do to really understand these things. So there's wonderful results that have come out, and just as one example, this is the spectra done with XMM of looking at, there's this one paper that had a number of different clusters where a line small sections of these clusters were evaluated, and then the wavelength plotted against the number of photons. You can see the data here, I believe, is in blue. The green is the best fit of kind of standard simple models that don't actually fit very well. As you can see, the simple cooling flow models that use our simple estimate of how we'd expect these clusters to cool would expect us to have all these elemental lines that actually you don't see when you look with the data. And this was a paper that I think Fritz Perls is here as well as Steve, of course. And by actually coming up with a more complex model, multi-component model, you can come up with a fit to really constrain these things much better. So I'm not going to get into much more detail there because there'll be a lot of talks about this sort of thing, but it's a wonderful probe. But the dream is, what if you could get this sort of data, but with much higher statistics? Large catalogs of clusters, two-dimensional images, what you could constrain would be very exciting. And really kind of the most interesting way to probably do that is to move away from these grating spectrometers that are these dispersive elements. They're still very valuable for some probes, but to be able to do these large statistic images, if you could just build large things like CCD cameras that actually gave you high spectral resolution at every pixel for every photon. That would be the dream. And the way to do that is to build these thermal detectors, X-ray calorimeters, where each individual pixel counts every X-ray that comes in and measures its energy. And then you can build these big arrays and get these wonderful images. And the interesting way to do that is to actually use a thermal detector. And so essentially anything that you can convert to heat, you can measure with a fancy thermometer. And all these are is fancy thermometers. Some block of material, when an X-ray photon comes in, it converts it into heat. So if you're plotting the temperature as a function of time, you'll see the temperature goes up, and then it'll relax back down to some bath temperature. And if you measure that temperature increase, and if you know the heat capacity C, then you know the energy of the photon, because the temperature increase is just going to be the energy divided by the heat capacity. And if you reconstruct that and get a data stream of all these little pulses, then you can do that. Two-dimensional images, high-resolution spectroscopy. Now, I believe that the actual first calorimetric kind of single particle, or I will say one thing, is that this is actually very difficult to do, because to measure the energy of an X-ray photon, an individual X-ray photon, to a part in several thousand, you have to have very accurate thermometers, and you have to get very, very cold so you don't have thermal noise. If you get very cold and use lithography, you can have very, very small pixels, but you also limit the thermodynamic energy fluctuations. And these energy fluctuations are essentially just caused by Brownian motion of heat. If you have a block of material here that's connected through some weak thermal link to a heat bath, just like you have Johnson electrical noise in a resistor, which is the Brownian motion of the electrons, you have Brownian motion of thermal excitations across that. And if you actually calculate that, the RMS energy fluctuations in that block of material will go as the square root of K Boltzmann temperature squared times heat capacity. So, and if you put in the numbers, to get down to these part in several thousand, you need very low temperature, like about 1/10 of a degree above absolute zero, and very small pixels. So the technology development has been able to build robust refrigerators that cool down to about minus 460 Fahrenheit, and that you can fly on a satellite. But that's all been done. And if you look back historically, I believe the first use of a thermal detector to measure quanta, I may be wrong about this, but the first I've been able to find, was actually done with a superconducting thermometer. And this was, I think, largely forgotten. But Donald Hatch Andrews in 1938 realized that you could use a superconducting transition as a very fancy thermometer and use that to measure very small powers and very small temperatures. And his idea here was that if you have a film that goes from a superconducting state with absolutely zero electrical resistance at some temperature to some normal resistance, in that narrow transition region, it's an amazingly good thermometer. And he used that for one thing to start looking at individual alpha particles and measure their energy, but he also used that to look at infrared signals. And this is actually quite remarkable. I found this from back in 1945. I believe this is certainly the first real-time infrared video camera. And what this is a single superconducting pixel that Donald Andrews operated in the lab and put in a little mirror that was scanning. And this is an oscilloscope. And this is in the dark. This is Professor Andrews at Johns Hopkins holding his hands up in the air in the dark while the single pixel scanned across him and measured his temperature. And that was so it was a real-time image. He could wave his hands and you'd see his image on the oscilloscope in 1945, which is pretty neat. So, but he also used these so that he built the first kind of infrared real-time bolometers, but he also built alpha particle detectors. He didn't yet use them for X-rays, but it's actually a very interesting historical note. And he was very ambitious. He actually had the vision that he wanted to put one of these in every car that was sold, so that you could actually see wildlife that was running in from the side. It was a little ahead of his time, but I'm sure that Google will do that eventually. Okay, so the first attempt to actually realize this vision, to actually put one of these, an array of these thermal sensors to measure an image of X-rays coming in and measure the spectrum of every single photon, and actually do it. It was actually done earlier by Dan McCammon in rocket flights to do it as a demonstration, but you just get a couple of minutes of data. So it doesn't give you more efficiency than these spectrometers. But this was the XRS instrument, which is, I believe, a 32 pixel. This was no longer a superconducting thermometer. This was using just a doped a semiconductor thermometer. So it's just basically a semiconductor where you measure a temperature change, still operated at 100 millikelvin. And this was flying on a Japanese satellite with a US calorimeter instrument made by Goddard Space Flight Center. There's a photograph of the satellite there before the launch. And here on the left is a picture of the instrument package, the 32-channel thing. This was actually on the cover of Physics Today in August of 1999, a very, very optimistic time. And that was a paper that I wrote with Carolyn Kilborn and Dan McCammon, talking about both this current generation and the next generation superconducting thermometers. And just several months later, it launched and ended up in the Pacific. So that didn't run so well. But to make a long story short, probably the first one will be successful next year. Astro H, the successor instrument, will be launching in 2016. So the dream is still out there, and I think we're very close to getting it. And there's a number of people in this audience who are our collaborators on this Astro H instrument. There are some history there, huh? that was a very, very difficult time. The second one, yeah, that was into my, to make a long story short. The second one actually worked in orbit on calibration spectra, but before they opened the gate, the cryogenics failed. So it's been a very difficult series of events. But Astro H, this time for sure. Now, something very good did come out of that XRS instrument on an Astro E. That actually, spare array was actually turned into a very robust instrument and was deployed in EBIT to do laboratory astrophysics at Lawrence Livermore. And I won't go into this much because I believe that there's a talk on this later by Bill Goldstein, Astrophysics in the Laboratory. And actually, these X-ray spectrometers combined with an EBIT, which is a device that can actually make astrophysical-like plasmas on Earth, things you normally wouldn't see on Earth, but plasmas where you would take like almost all the electrons off of something like iron, has allowed you to study these plasmas that normally would only be in space on Earth, so that you can develop all your models and develop all your knowledge. This is something that Steve's done a lot of, so that you will be able to interpret the data and derive your astrophysics and cosmology from it when you have something on orbit. So that will follow a bit later. I'm not sure if it's today or tomorrow. Okay, so but these are all semiconductor thermistors, and it turns out with a superconducting thermometer, which is kind of how these things were started, but then that was all forgotten. But you have the potential to do things that are a bit more sensitive, but also to make much larger arrays. And this is now sort of the state of the art in these X-ray spectrometer, calorimeter type sensors. And what these do is we're going back to Donald Andrews' idea of just using a superconducting film as a transition, but now we're using a lot of technology that Andrews did not have. One thing is he couldn't go very far because he didn't have very good amplifiers, because the Josephson junction hadn't yet been invented. And in the 1960s, a new type of amplifier was invented called a squid. And I'm not going to go much into this, but basically it is the analog of a two-slit optical interferometer, where you have the interference of two different light signals giving you kind of an interference pattern. In a similar way, you can actually have a quantum mechanical wave function that is modulated by a magnetic field that goes through it and give you an interference pattern, and that can give you a quantum mechanically accurate measurement of that magnetic field. And if you can measure magnetic fields very well, you can measure currents very well, because you can use them to make a field. Now, this sounds really complicated and exotic, but the wonderful thing about these superconducting amplifiers is that they like to operate cold. They like to operate at the same temperature as these calorimeters. As you recall, these things need to be at like 1/10 of a degree above absolute zero. Now, if you take like the sort of amplifiers that Andrews was using, or a FET amplifier, and you put it down to 1/10 of a degree above absolute zero, either it won't work or it'll just heat you up so much that you can't operate. So this really opened up an opportunity, along with some other complex ways. It really made this something that was practical to do. And it also, we've come up with ways to multiplex these amplifiers so that you can have one wire coming out carrying the signal of many different pixels. So now you can start making really big arrays. So this is the state of the art of these X-ray spectrometers now. These are now actually deployed in 256 pixel arrays. There's a photograph of one of these, and are doing high resolution spectroscopy at the level of sort of 2 electron volts, a little bit better than that, full width half max at about 6 keV, and now down well below an electron volt, full width half max, below a keV. Still not as good as you can get with some gratings down below a keV, but enough that you can do a lot of really good science, and many orders of magnitude more efficient. And that's actually showing a spectra of the development over the time of, this is actually hard X-ray detectors, going from sodium iodide. This is looking at, just as an example, one particular spectrum of an Earth-based sample. This is plutonium-239. As you can see, back with sodium iodide, you could kind of see this sort of blobby spectrum. cad zinc tel and cadmium telluride, you get better and better spectrum until you get to high purity germanium, which is getting really good. But then these transitioned sensor devices give you another step. Where the red is the high purity germanium, you get so much more information here. And it's even a bigger effect when you get down to the soft X-ray. So, and here's, I mentioned all these meetings that I've been to with Steve and Fritz and other people like that. So for the last 15 years, TESs have been baseline for the next satellite mission. And they still are. This was all the way from Constellation X back in 2000, the European Zeus mission, the Combined International X-ray Observatory, IXO, and now finally, Europe is actually going to fly one of these things. And this is like the Japanese Astro H calorimeter, but much, much larger. This is sort of a flagship scale instrument with thousands of pixels instead of just about 30. So now this is an instrument that should be flying now in 2028 that will be using TESs and will be able to do, for instance, with the clusters, high statistics. You could look at every cluster below some certain Z and get high spectral resolution images of whatever you want and really begin to nail this stuff down. But I think then the science that will be talked about more, I'm sure they'll be talking about AGNs and supernova remnants and things like that. And I think it's maybe not quite formally, but it looks like it's going to be a US TES calorimeter array that's flying on this European instrument. So that's something exciting as well, and we're hoping to be collaborators on that. So that's an exciting thing going forward. So I'm trying to figure out time-wise. I should now be starting my talk. So I think I can go through this, but I won't chew up all the extra time. I think we'll leave that for other people as well. So as I've said, there was this whole, just like there was this geographic migration pattern that Steve established, there's also been a scientific migration pattern from X-ray astronomy and X-ray astrophysics to cosmology. And the clusters are actually, one of the reasons I chose that is clusters are powerful both for X-ray astrophysics, but they are a tool for cosmology as well. But there's many other tools. And what I want to do is there'll be lots of talks about cosmology done with LSST and many, dark matter, dark energy, all those sorts of things. I'll talk a little bit about the transition to cosmology that my own career has had, where we realized as we were developing these X-ray spectrometers and seeing mission after mission to use them not actually get approved, that, you can do cosmology from the ground at other wavelengths. Isn't that exciting? Which is, I think, something that presumably a thought process that Steve may have gone through as well. And it turns out that these sort of superconducting sensors, you saw that Donald Landers back in 1938 used them to look at alpha particles, and he also used them to do this real-time infrared image. Now, that's amazing, a sensor that can do both. And in fact, these sensors are useful over something like 8 orders of magnitude of the electromagnetic spectrum. And they're useful that way simply because they're really stupid. All they are is thermometers. Like I said, anything you can convert to heat, you can measure with a thermometer, and the second law says you can convert about anything to heat. So here is pictures of superconducting transition-edge sensors designed to do science at many different wavelengths, all the way from about 100 keV hard X-rays and gamma rays to soft X-ray here, to visible photon detection, submillimeter, and this is one of our cosmic microwave background polarimeters. Now they all look very, very different. What's different, what looks different, is the way that they couple to the incident radiation. The thermometer and the readout electronics is really pretty much the same, and that means that you have enormous leverage. Once you've developed these X-ray spectrometers, you can actually build arrays of cosmic microwave background polarimeters. And it turns out that CMB polarimeters are really a lot easier. Because you don't have these pulses with high dynamic range, you've got these power levels which are nice and slow. And so we can make really big arrays. We've now made arrays of TSs at the sort of 10,000 pixel scale to do submillimeter astronomy and cosmic microwave background. And it turns out that over this whole range, by certain figures of merit, these sensors are interesting, are the best at what they do for different figures of merit. So there's going to be, like I said, there's a lot of the science that we're seeing kind of an overview here is being explored in more detail in later parts of this workshop. And Adrian Lee is going to be talking specifically about cosmic microwave background detection with TESs. So that's going to limit in how much detail I'm going to get into here. But I'll start by just showing these. This is a photograph of all the cosmic microwave background polarimeters that are in the field today. Although this is actually an old slide, that the ABS polarimeter is now decommissioned, and there's actually a BICEP 3 that's actually now beginning to operate in the field. But basically, there's a photograph of all of them, and all of the CMB polarimeters presently in the field use superconducting transition edge sensors to measure the incoming CMB and to measure the polarization of that CMB. And they use these sort of superconducting squid amplifiers that we developed to read out these large multiplexed arrays. And so we've actually provided, in some of these we've provided the sensors, and all of them we've provided the amplifiers to do this work. So transitioning from this X-ray work to the CMB has turned out, and doing cosmology has turned out to be a big success. So, kind of what people hear a lot about is looking for gravity waves from the Big Bang with the CMB, and that's an exciting thing, but the CMB is an extraordinarily powerful tool for constraining cosmology, which we've seen a lot over the last 20 years. And probably the most scientifically important thing that the CMB has done so far has been based on looking at its power spectrum. So here's a quick little reminder about the CMB. Is that the cosmic microwave background is essentially just the afterglow of the Big Bang. So we know that early on in the universe, there was some mysterious process by which the universe expanded very, very quickly and was very, very hot. And we're trying to understand the details of that. But the important thing is it was initially an extremely high temperature, and over a period of time, it's cooled. And what the cosmic microwave background is just the thermal radiation from that early very hot universe, but cooled down as the universe has expanded to the point where now it's very, very cold. It's about 3 Kelvin, or about 3 degrees above absolute zero. And if you look anywhere in the sky, this is the amazing thing, the cosmic microwave background is almost exactly the same temperature, even to parts of the sky that are so far apart that they're causally disconnected from each other right now. And that's because they're all kind of blown up from the same sort of Big Bang environment. Now it's not, but it turns out that it's not exactly the same temperature if you look everywhere. That the temperature at different parts of the sky varies at parts per million, maybe tens of parts per million. It's not exactly the same temperature. And by looking at that variation, you can actually learn a lot about the acoustic modes, the sound waves in that early primordial plasma. And there's an enormous amount of constraints that you can place on cosmological models. By studying those early sound waves that would have been kicked out by this early inflationary process from the Big Bang. Now, the way you look at these acoustic modes, at the sound waves, the easiest thing is to actually look at the patterns of hot and cold, slightly hotter and slightly colder parts of the cosmic microwave background. And the way we do that mathematically is we just look at the size of the spots and how hot and cold they are by doing something like a Fourier decomposition, where you kind of break, just like in a Fourier decomposition, you break things down into sine waves, either long period sine waves, which are things over long periods of time, over largely separated from each other in space, and high frequencies that are either close to each other in time or close to each other in space. And the way this is done is you actually look at the whole sky, you image the whole sky, and you break it down into spherical harmonics, which is a spherical version of a Fourier transform. And that's what's plotted in the y-axis, is the intensity of each spherical harmonic. The x-axis is that spherical harmonic, or it's the inverse of the size on the sky. So that first peak right there is at about the degree scale. And if you look at about a degree part in the sky, it turns out there's hot spots and cold spots. But there's also hot spots and cold spots as you look at smaller scales and smaller scales and smaller scales. And that's all predicted by the patterns of these sound waves from the Big Bang. So the best large-scale measurements have all been done by initially WMAP, but now by the Planck satellite. And the Planck satellite was using thermal detectors, like we're describing, but the older style semiconductor detectors. And Planck flew a couple of years ago, but with a satellite, you always freeze in technology from a long time ago. And the best information at these low frequencies was all produced by that, whereas the high frequency information is all taken from 2 ground-based transition sensor-based CMB detectors, the Atacama Cosmology Telescope and the South Pole Telescope. And this is all taken from one of the Planck papers. And it's all being used now to constrain a lot of what we know about the universe. So that's another great success. And what I won't go into is the very exciting things you can do by starting to look at not just the temperature of the cosmic microwave background, but its polarization, kind of which direction the electric field is wiggling. And if you actually look at circular patterns in the cosmic microwave background, you can start constraining not just these early acoustic modes, but you can look at the Holy Grails, looking for gravitational waves from the Big Bang, and also you can start probing a lot of new things about cosmology, a lot of new probes of neutrino mass and the number of neutrino-like relativistic species and things like that. So I'll just show this one plot showing here were these acoustic modes that you saw in that previous plot, this temperature anisotropy. And now we have to look at orders of magnitude more sensitively to look at the polarization signals. And Adrian Lee will be talking about this in focusing on that in his talk tomorrow. So I won't go into great detail about that. But again, this is all using the same sorts of thermal detectors. And there's lots more science to be done to actually extract everything from here. I think that to get the ultimate information from this would require both a large suite of very large ground-based telescope arrays and possibly also a satellite as well. And so one thing we're working on at this point is to, just like Steve has gotten the DOE involved in the LSST type stuff, is there's now been a lot of work towards getting the DOE involved in the constraints that you can place on inflation, neutrino mass, all these sorts of things by building much larger arrays of CMB bolometers. And it looks like we need somewhere between maybe 100 or 200,000 and 500,000 individual sensing elements on telescopes, both small and large scale, to really get down to the point where you can measure cosmologically the neutrino mass and the search at the optimal level for these gravitational waves. And that's actually, there's a lot of technology development there. That shows one of our CMB polarimeters now that is now doing multicolor measurements, where you're not only measuring the power and the polarization at one frequency, but at several frequencies. This one does both 90 gigahertz and 150 gigahertz. This is a niobium antenna where you have the signal coming in, then these little antennas break it into the X polarization and the Y polarization, and each one of them flows through a different filter bank to pick off a different frequency. And as you see, this one pixel has 1, 2, 3, 4, 5, 6, 7 different transition sensor thermometers. So a lot more complexity, but it's pretty exciting. Okay, so I guess I'd need some guidance. I can actually now try to stick to that sort of 30 to 40 minutes or chew up some of our time. Tom, what do you think? Should we save 5 or 10 minutes? 5 to 10 more. Okay, 5 to 10 more minutes. Okay, so I'll do 5 more. Why don't I jump ahead? You can also, I won't discuss. You can also use the CMB to do more cluster work, but I'll jump ahead to talk about some of that beyond stuff because that's exciting as well. I talked about using these thermal detectors for X-ray astrophysics. We've discussed that. Now for cosmology, especially I've highlighted using it to study the cosmic microwave background and constrain cosmology that way. But one of the exciting things is how these same sensors we've developed for this can also be used for the other major focus of SLAC, which is these X-ray beamlines to do probes of chemistry and biology, condensed matter physics, materials, third-generation photovoltaics, all that sort of thing. And it turns out that just like you can get the high resolution of a grating, or close to it, but much more efficiently in a satellite, you can actually get close to the resolution of a grating on the ground, but with orders of magnitude more efficiency. And that means that there's really some interesting things you can do at light sources, like the Stanford Synchrotron Radiation Laboratory that's here, and also the LCLS, free electron laser. And what I'll show you is just a couple of things. One is sort of a prototype of taking these X-ray spectrometers developed for astrophysics and putting them on a beamline, This is some data we have, and also an example of the potential going forward. So this is actually one of these spectrometer arrays we developed for astrophysics. This is a picture of that refrigerator I described that gets you down to 1/10 of a degree above absolute zero. It's actually more like 20th of a degree above absolute zero. And this is now a commercially available, liquid cryogen-free magnetic refrigerator. It's actually a mechanical refrigerator that gets you down to about 3 degrees above absolute zero, and then a magnetic refrigerator that gets you all the way down to about 50 millikelvin. It's a turnkey sort of thing. The thing that used to be so hard and so exotic, you can now buy one of these things and put it on an X-ray beamline and run it sort of automatically. And so inside that metal box, there's a cold stage that's at 50,000th of a degree above absolute zero, and there's a finger, a little copper cold finger that sticks out through this little snout that you see there, this bellows, and that sticks into this sample chamber that's mounted actually on the NSLS at Brookhaven. It's a synchrotron at Brookhaven. And what we've done here, which is this initial work we were doing, was a forensics application. And this is to actually study the X-ray spectra of nitrogen when it's in a different chemical bonding environment. The two that are interesting here are RDX, which is a component of C4, a chemical explosive, and ammonium nitrate, which is used in a fertilizer bomb. Now, what you really want to be able to do here is actually find out a way to just take a nondescript white powder, where you don't know what it is, and very quickly figure out if it's anthrax or if it's C4 or something like that. Something comes in an envelope or something like that. And one way to do that is with X-ray spectra. And in fact, if you can do it with X-ray spectra, about every forensics lab in the country has a scanning electron microscope. And scanning electron microscopes, when you hit things with electrons, they fluoresce X-rays. But when you've only got sort of nitrogen and oxygen and hydrogen and carbons and things like that in these molecules, and everything organic has those. So to be able to actually figure out what threat material you're dealing with, you have to be able to look at very high resolution and look at the shift of these X-ray lines. So this is looking at a small sample of RDX which is used in C4 on this beamline, and also some ammonium nitrate. And this is a nitrogen excitation line, the fluorescence at about 390 electron volts from nitrogen. And as you can see, at the sort of resolution we're able to get with these sensors, the nitrogen lines look completely different based on their chemical bonding environment. The nitrogen in the ring and RDX gives you kind of a broad peak with a tail down here, whereas in ammonium nitrate, you've got two different nitrogens that are in two different environments. You get 4 peaks actually, which is expected from the theory. And if we can now take this sensitivity we've demonstrated on the synchrotron, put it on a scanning electron microscope, it's a possible forensic tool. I'll give you one more example of this, and then we'll hand it over. Then this is the sort of thing that you could look forward to doing on a free electron laser, the LCLS, something a little bit more complicated. So a free electron laser is an X-ray source that also comes in a very, very short pulse, in less than a picosecond, maybe hundreds of femtoseconds. And this allows you to do things where you do pump probe experiments, where you take an interesting material, you shoot a laser at it, optical photons, then you wait a period of time and whack it with X-rays and try to figure out what is happening, how that molecule is reacting to light. And that's interesting to do, for instance, for photosystem 2, which is a protein involved in photosynthesis. It also is other photoactive things, including photovoltaics. So here's one example of something that we're working on being able to do. This is actually a 3rd generation photovoltaic, so it's no longer a semiconductor, high efficiency thing. It's also not a kind of low efficiency, cheap thing. The idea of a 3rd generation photovoltaic is something that will have the high efficiency of expensive 1st generation photovoltaics, but are cheap, mass producible, flexible, things like this. One candidate for that is dye sensitized photovoltaics. And these organic molecules with an active metal that connect to an electrical circuit. And one that's actually commercially produced, that is actually flexible, that you can actually get on, I think, on a backpack at this point, uses a complex molecule with several ligands and an active ruthenium ion in the middle, as well as some manganese. And what happens is when the optical photons come in from the sun, they promote an electron on sort of picosecond timescales from this manganese complex to this ruthenium complex. And then you have to figure out a way to get the electron to go out one of these ligands and then connect to your electrical circuit and kind of flow around, complete the circuit, and use that as an alternative way to generate power. And this works, but it works, it's flexible, but it's low efficiency, and with ruthenium is not an incredibly cheap ion. And what you can't do with the simplest probes that we have is try to understand all the individual steps here, because many processes compete. If you have an electron go to the ruthenium, it can then go to this ligand and then go out and complete the circuit. It can get trapped on a ligand you don't want to get trapped on. It can go back to the manganese. And all these events occur on picosecond timescale or sub-picosecond timescales. And so with the high resolution spectroscopy, you can actually look at the X-ray emissions from that ruthenium, and you can figure out how it bonds to all the nitrogens around it, what the ionization states are, what the spins are, and really resolve and exactly where the electron goes. What are the probability that it will go here, or go back to manganese, and independently optimize each of these individual steps. And so by building a large enough, sensitive enough array, putting it on the LCLS, hitting it with an optical photon, and then looking at, with a high efficiency at the spectroscopy of that ruthenium, we have the possibility to improve the efficiency. You could also have the possibility to maybe replace that ruthenium with something else like an iron, figure out a way to make that work as well. So that's an example of the sort of problem you might be able to solve with these, what we're looking at towards the future. So what I'll just leave it at is, that's been kind of my migration path, which is different, but has some similarities to what Steve has done. I think what we'll see in the rest of this workshop is really fleshing out all the sort of different areas that Steve has looked, new areas that he's looking, and all the exciting sciences there. So, thank you very much.
Questions or comments for Kent?
May I ask a really detailed question?
With the mic.
It worked? Okay. So the fluorescent emission line spectroscopy,
Yes.
right? The different shapes for the different environments that
Yes.
elements are in. How specific is that? How many different kinds can you tell apart?
And the answer is that's an active area of research. And
That's what I thought.
NIST, so to NIST, where I was at up to a year and a half ago, one of their roles is not only developing this measurement technology, but also developing these large databases. And the question is you got this high resolution spectroscopy, but you're starting to deal with these sort of gooey materials. It's not these nice crystals. When you have a gooey material, things kind of get more complicated. And what we need to do is build up large databases of many, many molecules looking at many, many materials. And so the reason why we did this, built this instrument for this beamline as a synchrotron was so that they can actually build that database. And this was sort of an example, but now they're going to start cycling through many, many molecules, and you have enough efficiency to do just large databases. It looks hopeful. Now we're about 2 times better energy resolution than we had there. I think this was an example. There's a lot of molecules that you can't tell apart quite as easily, but I think we're with about a factor of 2 better. I think we're getting to the point where it could be broadly useful for forensics. Yeah.
Sounds great.
So Kent, one of the advantages or disadvantages of X-ray astronomy is our photon rates are really low, so you can
Yes.
have long pulses without piling up.
Yes.
As you go to the synchrotrons and LCLS,
It's a lot harder.
It's a lot harder.
Yeah.
Do you have to make the pulses very short to avoid that, or you
So,
just
well, it
have small-
depends. First of all, it depends. It's a very different answer for an FEL than for a synchrotron. An FEL is sort of maximally bad. In some ways, that makes it easier. A free electron laser, it's not just that the photons come close together. They all come essentially at exactly the same time in your pulse. So in the case of a free electron laser, you just have to be fast enough to tell apart one frame of pulses from the next. With LCLS1, that's only 120 hertz. LCLS2, the hope is to get that up to like a megahertz, which is crazy fast. but nobody else can detect that either with the big imaging arrays. But with LCS1, the way you get the high data is actually by having large numbers of pixels. Making your pixels faster doesn't help. Right now, so we're working now towards kind of having we'd like to build a prototype instrument at the kilopixel level, and it turns out whether that's enough to give you the statistics on that one pulse or not is wildly dependent on the scientific question. Every scientific question has a totally different requirement. Like, we're studying that right now. So if we're looking at one of these, a particular photosystem 2 problem, I think the decision is to be an order of magnitude faster in getting your data than the bent crystal spectrometers they're using now. We would need 3,000 pixels. But that answer is totally different for different lines and different problems. With a synchrotron, yes, you need to be fast. And in the end, there are problems that you're just not going to use this technology for. But there's a lot of them that has enormous impact.
Just a quick practical question. You've been talking about numbers of pixels. Yes. I'm extremely interested in sizes of pixels.
Yes.
Could you comment on where that's going?
So, do you want them small or big?
Small.
Small, okay. So, we can make the pixels quite small. Right now, it's a question of getting the leads out of the focal plane. So for a small enough array, we can make pixels as small as maybe 10 by 10 microns, linear array. But then you can't get the wires out if you're making a big two-dimensional array. So at the kilopixel scale, we can certainly get the wires out if they're spaced at maybe 200 microns between pixels. And for an arbitrarily large thing, what you'd really like to do is having a multiplexing element in the area of each individual pixel. And we haven't done that, but I think I know how to do that with sort of 300 micron pixels. How to do it with 20 micron pixels, I have no clue. There need to be some new ideas. That's another limiting factor.